Have you ever really thought about what happens to a Java object like the second after you type new? Where does it actually go? And how does Java just magically clean up all that memory without you having to do a thing? Well, today, we're going to pull back the curtain on Java's garbage collection. We're going to follow the life of one single object, from its super fast birth all the way to its final cleanup. So let's get into it.
So here's the game plan for our object's big adventure. First up, we'll talk about why we even have garbage collection in the first place. Then we'll watch our object get created and immediately face its first big test in what's called the generational divide. We'll see if it can survive long enough to make it to the old generation, meet the different managers that run the whole show, and then most importantly, we'll wrap up with what all this techie stuff means for you, the developer.
Okay, so before our object even exists, we need to understand the why. Why go to all this trouble for automatic cleanup? What was the huge problem that garbage collection was invented to solve?
And this slide, right here, tells the whole story. You know, back in the day with languages like C++, it was all on you. You created memory, you had to remember to delete it. If you forgot, you got a memory leak, your application would just eat more and more memory until it crashed. If you deleted it too early, bam, another crash from a dangling pointer. It was a minefield. Java, on the other hand, just said, you know what? Let's take that whole burden away. The JVM is now responsible, which makes our lives so much safer and more efficient. No more manual cleanup. What a relief.
All right, it's time. Our object story is officially beginning. It's about to be born into the Java heap. And you might think this is a complex, slow process, but it's actually the opposite. It is lightning fast.
So how can it be so quick? Well, our new object isn't just tossed into some chaotic shared free-for-all. Nope. It's born inside something called a Thread Local Allocation Buffer, or TLAB. Think of it as a small, private nursery just for the current thread, located in a bigger space called Eden. To create our object, all the JVM has to do is bump a pointer forward. That's it. No locks, no fighting with other threads for memory space, just pure, unadulterated speed.
Okay, our object is alive and well in Eden, but life here is intense and often very short. It's about to face its first trial by fire, because the whole Java memory world is built on one simple and kind of brutal truth.
And this is that truth, the generational hypothesis. Basically, the JVM knows that most of the objects we create, think temporary variables in a loop or a string you're building, they're used for a split second and then they're done. They die young. So it would be a huge waste of time to constantly check every single object in the entire system. Instead, the garbage collector smartly focuses most of its energy on these newcomers because that's where the most garbage is going to be found.
So here's how that first test goes down. Your application is just humming along, creating objects until, bam, Eden is full. This triggers what's called a minor GC. The whole application pauses for a teeny tiny fraction of a second. In that moment, the GC traces everything that's still actually being used, the live objects, and copies them to a safe zone, a survivor space. Everything else left in Eden, it's considered trash, and the whole space is just wiped clean. Our object, if it's still needed, just survived its first brush with death.
But what about the objects that stick around, the ones that don't die young? Well, if our object keeps proving its usefulness, surviving one minor GC after another, getting copied back and forth between these survivor spaces, it eventually earns a promotion. After a certain number of survivals, it graduates to the big leagues, the old generation, the part of the heap reserved for long-lived, tenured objects.
Now, life in the old generation is a lot calmer. Cleanup here, called a major GC, is way less frequent, but it's a much bigger deal. It kicks off with a short pause to mark the most obvious survivors. And then, this is the really cool part, the GC does the huge job of tracing all the other live objects while your application keeps running. It's working in the background. Then there's one more super short pause, the remark, just to catch any last-minute changes, and finally, the garbage gets cleared out and the memory gets tidied up.
So, who are these magical workers doing all this cleaning? Well, there isn't just one garbage collector. You can think of them as different managers of this whole memory city, each with their own unique style and strategy for keeping things clean while causing as little disruption to the citizens, your application, as possible.
The one you're probably using right now, maybe without even knowing it, is the Garbage First, or G1 collector. It's been the default since Java 9, and it's really smart. G1 chops up the entire heap into a bunch of small regions, and instead of trying to clean the whole city at once, it looks around and says, which neighborhood has the most trash? And it cleans that one first. This clever garbage-first approach lets it meet predictable pause time goals, making it a fantastic choice for most applications. But hey, sometimes predictable isn't good enough. For things like high-frequency trading or massive real-time systems, you need pauses to be almost non-existent. That's where these specialized collectors come in. You've got ZGC, which aims for just insane sub-millisecond pauses. It uses really cool tricks like colored pointers to move objects around while your app is running. Then there's Shenandoah, which also focuses on ultra-low pauses that don't get bigger even if your EAP size is massive. They all have the same goal: keep those stop-the-world moments as short as humanly possible.
Oh, and one quick pro tip about G1 before we move on. If you ever create a truly massive object, we're talking a giant byte array that takes up half a memory region or more, G1 calls this a humongous object. It handles it specially, but it's something to be aware of, because creating a lot of these can sometimes lead to wasted space, or what we call memory fragmentation. Just a little something to keep in the back of your mind.
Okay, we've seen our object's entire life story. We've seen how it's born, how it survives, and how the system eventually cleans it up. So now we get to the really important question: what does any of this mean for the actual code you sit down and write every single day?
Let's just get this one out of the way first, because it's a classic mistake. You might see code out there with system.gc in it. You need to know, this is not a command. It is at best a polite suggestion to the JVM, and honestly, it's usually a bad one.
So what is your job then? Well, your main job is to let the garbage collector do its job. Write clean, simple code. The biggest favor you can do for the GC is to not hold on to objects you don't need anymore. This is called avoiding lingering references. If you're done with an object in a big static map, for example, remove it. Also remember, GC handles memory, not things like files or network connections. For those, you absolutely have to use try with resources to make sure they get closed. And seriously, trust the collector. Calling system.gc yourself can actually make performance worse by forcing a huge, expensive cleanup at the worst possible time.
And speaking of bad habits, here's a quick update from modern Java. You might have heard of an old method called finalize. People used to try and use it for cleanup tasks. Well, don't. It's been deprecated for a reason. It was unpredictable and caused all sorts of problems. The right way to handle cleanup today is with try with resources, or, for really advanced scenarios, the Cleaner API.
So there you have it. We followed our little object all the way from a quick pointer bump in a TLAB to a sophisticated cleanup by a collector like G1 or ZGC. The whole thing is this incredible, evolving dance of optimization that's been refined over decades. Which, of course, leaves us with one final fascinating question to think about. Now that you see how far it's come, what do you think the next generation of automatic memory management is going to look like?